Hello everyone, I am Ladeeda from MES Ponani College. Today I am here to speak about energy and power of a mechanical wave. First of all, let's look the concept of wave. What is wave? In the language of physics, a wave is the propagation of energy. For example, we have water waves, electromagnetic waves, etc. in nature. A schematic representation of the wave is shown in the figure. Each particle in the wave is engaged in transferring energy from one point to another. Mathematically, wave can be expressed as y of xt is equal to a sin kx minus omega t. Here, I am planning to compute the power of a mechanical wave. As we all know, power is the amount of energy being transported per unit time. The total energy is composed of both kinetic and potential energy. That is, E total is equal to Ke plus Pe. Now let's move on to kinetic energy of the wave. Kinetic energy is the energy due to the motion of the particle. Particles are moving in vertical direction and there is kinetic energy associated with this motion. In this figure, we can see that each particle is moving in the up and down direction and we are going to calculate the kinetic energy due to this simple harmonic motion. For that, let's consider a small element of a string having mass delta m. Each mass element delta m of the string can be considered as a simple harmonic oscillator. Here we define a term mu as the constant linear density, that is mu is equal to dm by dx. The equation of the kinetic energy is half mv square, which for the elemental mass dm is dke is equal to half dm vy square. Substituting dm as mu dx, we get dke is equal to half mu dx vy square, where vy is the vertical velocity of the particle in the wave. Now we have to find out what is vy. So we have a sinusoidal wave with an angular velocity omega given by y of xt is equal to a sin kx minus omega t. To get Vy, we have to differentiate it with respect to time, and that is Vy is equal to dy of xt by dt is equal to minus a omega cos kx minus omega t. Substituting Vy in the previous equation, dke becomes half mu dkx into minus a omega cos kx minus omega t whole square. Finally, we get the expression for kinetic energy of the elemental mass, that is dke is equal to half mu dx a square omega square cos square kx minus omega t. This is the instantaneous value of kinetic energy and we can see that it is time dependent. Now let's calculate potential energy of the wave. When the wave propagates through the medium, the particle experiences a certain amount of deformation which is stored as the potential energy. The length of the wave increases slightly during the transverse moment. This leads to the deformation of the string. Now we have to find work done on elemental region given by dW of y is equal to tension into change in length. This is the common equation for the work done, that is work is equal to force into displacement. Here force is the tension over the string and displacement is the change in length. That is dw of y is equal to tension into ds minus dx. ds minus dx easily find out from the figure. This is clear that dx is the original length and ds is the new length upon stretching dx. Now we can apply Pythagoras theorem. Here ds can be approximate as a line and we can write ds square is equal to dx square plus dy square. After rearrangement, ds is equal to dx into 1 plus dy by dx whole square all raised to 1 by 2. To expand it, we use binomial theorem given by 1 plus x all raised to n is equal to 1 plus nx plus n into n minus 1 by 2 factorial into x square plus etc. In our context, x equal to dy by dx whole square and n is equal to 1 by 2. And dy by dx is very small due to fast motion of the wave. So we can neglect the higher terms like x square, x cube, x raised to 4, etc. After the expansion, we get the simplified equation that is 1 plus dy by dx whole square all raised to 1 by 2 is equal to 1 plus 1 by 2 into dy by dx whole square. Using this and after arrangement, ds minus dx becomes half into dy by dx whole square into dx. Substituting these ds minus dx in the previous equation, the equation becomes dw of y is equal to tension into ds minus dx, that is t into half dy by dx whole square into dx. Here we have to get the dy by dx. To get that, we use the wave equation dy of xt by dx equal to ak cos kx minus omega t. Substituting it for dw of y is equal to t into half ak cos kx into omega t whole square into dx. This is the expression for work done and this work done is stored as the potential energy, that is dPe of y is equal to half T a square cos square whole square kx minus omega t into dx. Now we calculate the instantaneous energy. I have shown the expression for GKE and dPe calculated in the previous slide, and the instantaneous total energy is given by dE total is equal to dKe plus dPe. Substituting these dKe and dPe in this equation and taking common terms outside, we get dEt is equal to half a square cos square into kx minus omega t into mu omega square plus tk square into dx. We know that velocity of the wave is v is equal to root t by mu, that is t is equal to v square mu. T is the tension and v is the velocity, mu is the linear density. And this is the another equation of the velocity of the wave from the wave equation, that is v is equal to omega by k. Here omega is angular velocity and k is wave number. Combining both equations, tk square is equal to omega square into mu. Substituting it back to the expression for the total energy, it becomes half a square cos square kx minus omega t into mu omega square plus mu omega square into dx. And finally, we get total energy, that is dEt is equal to a square mu omega square cos square kx minus omega t into dx. This is the total energy contained in a length dx of the oscillating string. Now we are coming to our goal, that is power. Power is the energy transported in unit time. So we got the instantaneous total energy, that is dEt is equal to a square mu omega square cos square kx minus omega t into dx. Dividing both sides with dt, it becomes P instantaneous is equal to a square mu omega square cos square kx minus omega t into V. Here V is equal to dx by dt. This is the instantaneous power, which is time dependent. This is not a measurable quantity. The measurable quantity is the average power. To get average power, we have to integrate over time period of the wave capital T. P average is equal to 1 by T integral of 0 to T a square mu omega square cos square kx minus omega t into V dt. And we get P average is equal to half a square mu omega square V. This is the measurable average power. So, in this presentation, we have obtained the expressions for the instantaneous total energy, instantaneous power, and average power of a mechanical wave. So, I hope you enjoyed it. Thank you for listening.